Looks like I'm going to have to hold my microphone. The clip. Is this working? Good. So, Monty Python says, now for something completely different. This isn't very theoretical. This is actually very practical. I'm an engineer and I like the science stuff. It turns out that you can use the Bayesian inference framework for design because, at least in my view, design is just another inverse problem. And even though I don't think really design is inference, the mechanism, the structure of the problems are very, very similar. So you can use the mechanism of Bayesian inference to do design, and that's what I talked about. I've talked about this before, the first time in Brazil, and then my graduate student gave a talk in Oxford in 2009. You found the clip? Thank you. Today I'm going to talk about the inference-based design of finite impulse response. Filters of a particular sort, filters that have coefficients that are made up of the sum of assigned power of two coefficients. The significance of this is that digital filters are often used in real-time systems. And as sampling frequencies go higher and higher, it gets more and more difficult to design a filter that can actually work in real time. And these filters that have coefficients that are the sum of assigned power of twos are capable of doing the calculations required in the filtering quickly enough that the filter can operate in real time. So I'm going to start off with sort of a tutorial and a lot of discussion about the filter so that you can understand the model. That's actually, I think, the difficult part. Then I'll talk about how it is that you assign the likelihood to the parameters of the filter. I'm sorry, not the parameters, how you assign the likelihood to achieve the amplitude response you want, but also critically how you assign the priors that enforce the constraints on the parameters, design parameters of the filter. Let's see if I can make this work. So a little bit about analog filters before I talk about digital filters. A filter, an analog filter, is just a linear time invariant system. And you can represent it this way, where x of t is your input, y if you get your output. And if it's linear time invariant system, you can represent with an impulse response h of t. And in the time domain, you can write the output, which is the convolution of the impulse response. And the input, I started this at 0 because I assume I have a causal filter. A non-causal filter, you just start at the lower limit at minus infinity. We're usually interested in looking at filters in the Fourier transform domain. So if you take the Fourier transform of this convolution relationship, you get this. So capital letters of the Fourier transforms, and this h of f is the transfer function of the filter. Usually in signal processing, you want a filter that has a time delay that's independent of the frequency of component of the input. This is so that you don't get distortion of time domain pulses through the filter. And so you can achieve this if you take, this is a complex expression, h omega, sorry, I'm the wrong way. If you take this and write it in polar form, you look at the angle of the phase, if that's a linear function of frequency omega, then you're guaranteed that the time delay through the filter is constant. And you can establish this by the topology of the filter. So what you're left to design is the amplitude response. So you look at the magnitude of the transfer function, and here is just what you might wish to achieve. This is an ideal low-pass filter, so it's 1 over some pass band up to some omega p of the pass band frequency, and then it cuts off anything at a higher frequency entirely to 0. Of course, a filter like this can't be achieved, but often you'd like to achieve this sort of filter, at least do the best you can. So I'm going to talk about the design of digital filters here. And you can write a similar convolution expression. Let me first say that here I'm using time as an integer here, so we've taken time, whatever it really is, and we've normalized by the sample period, the sample time. So the t here is an integer. And the filter looks, a finite impulse response filter looks like this. You've got your input, and then these are the minus ones are a unit delay, so each one of these, but this is E of t, this is x of t, this is x of t minus 1, x of t minus 2, so forth. So you've got the delayed input, and then the output you get by taking these various delayed forms, multiplying by a coefficient, and then summing up all of those results to get the output. And so this YT, this is also actually a convolution, discrete convolution interval. Here, I've got a filter that's got odd symmetry of these coefficients. So this is C0 in the middle. C1 is actually a coefficient on either side. And this odd symmetry guarantees your linear phase of your transfer function. So I picked a topology that guarantees the phase I want. So what I'm left to design is the magnitude or the amplitude of the transfer function. Of course, the length of this filter is, there's actually only capital K plus 1 of these coefficients. So K is sort of the half length of the filter. The total length is 2K plus 1. And I've taken equation 1 and I've rewritten it this way. So instead of having to pull this single term from this C0 here, I can put it inside and sum from K is equal to 0 to K. And I've done this just by finding this cap function. Right. The problem with this filter, as it's written from the point of view of trying to make a filter that's going to work in real time, is that multiplications are very expensive in time. And so to actually implement this filter, I've got to have actually 2K plus 1 multiplications. And if you're trying to do this in a sample period, that's often not possible if you're talking about a very high frequency of operation. And so to get around this, you can do something a little different to generate these coefficients. And I'm trying to illustrate this here. Whereas you can't multiply very quickly, it's very easy to take a binary number and divide by 2 or divide by 4 or divide by any power of 2. You just shift the binary point. And so in place of multiplying by C0, I can take, for example, I'll take this x of t minus k, and I can divide it by some power of 2, negative power of 2, so I'll divide it by half or fourth or an eighth or something. And I'll either add or subtract it when I come in here. And I'll have some number of these terms, and I can build up, well, not every value of C0, but a lot of values of 0. So I can make my filter coefficients that way. And so my C0 is going to be the sum of some of these sine power of 2 terms. Does this make any sense? Right, so I don't know how many there are. One of the things in this design is I'm going to determine how many of these terms and what their values are. So here are the possible values of these sine power of 2 terms, again, from -1 to 1, and then minus a half, so forth. And I'll limit the range of these things so that the smallest magnitude of my sine power of 2 is 2 to the minus b, and b is just something I choose to avoid having to shift my word more than b bits. And this is also kind of important to control this number because you don't want to have your word size larger than it needs to be. It makes the filter more complex than it has to be. So looking back to the equation for the output of the filter on the previous slide, here it is in terms of the c sub k's, and here it is in terms of the sine power of 2 terms. And there's something important that happens here. In this equation, k is a parameter, little k is not a parameter, it's an index. Here, I'm summing over n. Here, n is the index. This thing that looks like k is t sub n, but t sub n is a parameter and it maps the values of k. But there's no real relationship between n and the index. So t sub k tells me what tap position k a particular sine of power of 2 term goes with. So here again is the relationship of those. Let's move those two equations. If I want to know a particular coefficient of my filter, I have to sum over some number of these sine power of 2 terms where this t sub n is equal to k. And of course, if I have determined those, if I have a designed filter, I can get back the filter half length by looking over all the p's and k's and finding the one that's got the largest value. And that again sets the total filter length. And the total number of sine power of 2 terms that I have to multiply to is something I'm interested in, because again, this partly determines the complexity of my filter and how quickly I can make these calculations. And that's actually twice the number of sine power of 2 coefficients. And I have to subtract. I have an extra one from the odd symmetry, so I have to subtract off the number of sine power of 2's going with the center coefficient. Okay, well, what I'd like to design about this is the amplitude response. And so I can write the amplitude response in equation 8 for the coefficients of the standard sort of filter, but I can also write it in terms of the sine power of 2 coefficients. So here, if you will, is the model. This is the thing I'm trying to design for. And here, theta is dimensionless digital frequency. So essentially my sampling period is 1, so the maximum frequency is pi. And I actually want to, my specification is typically given in dB, so my model is actually the log of the amplitude response. I don't care about the passband gain of a digital filter. I can adjust for that later. So this is normalized by the passband gain. So this is actually, if you will, if this was a model selection problem, this would be the model. All right, so here's my design goal. And I'd like, in this example, to get something that's as close to an ideal low-pass filter as I can get. So I allow some ripple across the pass band. And then I allow some frequency region to go from the pass band to the stop band. And I'd like this thing to be below some value, so past the stop band. And my design goal, well, I need to find the number of some sine power of 2 terms required to implement this filter, and I need to determine their values and which filter cap they go with. So these, if you will, these are the parameters I'd like to determine. Well, I've gone a long way without talking about any inference. It takes a while to describe the model, but here's my base theorem, where those upper and lower envelopes describe my desired amplitude pattern. These take the place of my data, if you will. And so here are the parameters I'd like to infer: the number of sine power of 2 terms, and then the values of all the filter coefficients. And this is given my desired amplitude response. And I have to define some sigma that tells me how much I'd like to, how important it is to meet the requirement at each step frequency across the range. So I need to assign the prior parameter to enforce design requirements, or at least design goals and desires. If I set the prior on the number of sine power of 2 terms, I can control that as to uniform 0 to 50 in the examples I'm going to show you. The prior on this parameter t sub n, that's the pointer to the taps on the filter. I'm going to set that to 20. This sets the maximum of my filter, and this is something actually I usually do want to have a hard constraint on. This one is maybe looks looks a little strange the way we assigned prior for the values of the sum power of 2 coefficients. It's done this way because actually I want to discourage very small values. So I've chosen this distribution so that it renders SPOT terms having large values of p sub n less probable. And again, this is because if I can, I want to design this filter so that I don't have to do any more shifts of the values than I have to. This helps reduce the complexity of the filter by lowering the word size that's required to implement it. Although I do have a hard lower limit that I set to 10 in these examples. Likelihood is assigned based upon the error, just as we usually would assign here. But here, it's the error of this log amplitude response for the filter. And I just take the difference. If it's below the lower limit, I assign how much below is the error, and if it's above the upper limit, I assign this as the error. If it's between them, I just say 0 error. And then I give at each frequency point, I assign this a Gaussian distribution with some sigma. And it's just something I have to set. And I just say they're independent. And this gives me the overall likelihood. Okay, well, we set it up this way. And, once you've done this, if you have a powerful MC routine, we use John Skilling's basis, well, just turn the crank and out pop the samples from the posterior distribution, and each of these samples ought to be a design candidate. It ought to be able to meet these requirements to a very good degree, some of them nearly perfectly. Okay, we did this, and guess what? It didn't work. It didn't work.
What do you expect?
I expected it to work. I expected that it would work the first time I do it. No, not really, but we've done this with other things, and this with antenna arrays, and this was all that was required. Yeah, well, the problem is that you're actually forming these coefficients from the sum of these sine power of 2's, and there's a huge number of redundant combinations of these things that will give you any particular value of that. And that turned out to be the problem. For example, if 2 terms have the same power but opposite sign, well, clearly they just sum to 0. Or if you have 2 terms of the same sign, but a power and the same power, well, clearly they just sum to, but clearly they just sum to one that's a single term that's at 1 greater power. Similarly, if you have terms with sequential powers and opposite signs, you can rewrite them as a single sine power of 2 term. But here's actually the real killer. If you have 2 terms of the same sign and sequential powers, you can rewrite it this way. That doesn't look like a problem, but it turns out to be true for 3 sequential terms of the same sign. You can write as 2 or 4 or 5. All right, so here's an example or 2, but again, it's runs of these things that are the problem. These are, the way to do this really would be to, since these are parameters, it would be nice if you could deal with this with a prior. But if you're going to use basis, you can't, because you've got to have an atomic prior, and this would be parameters of different atoms being related, and that you can't do that. So we want to find the likelihood to suppress the problem. We just go through and count up the number of occurrences of one of those 4 cases and call it R. And then we add a penalty term to the likelihood. And of course, we have to also assign it some sigma, but it turns out not to be terribly important as long as they're close in magnitude to the sigmas you assign for the quote-unquote data, then this works just fine. And I already really talked about this. After you got your samples from the posterior, you got 3,000 samples. You still, many of those could be your design. So there's a decision aspect. You have to decide which one, and our decision you can do it a bunch of different ways. Here we first selected all the design candidates that had 0 or minimum error. Here, in the example I'm showing, we get many with 0 error. So they perfectly meet the amplitude requirements. Among those, we choose the ones with the fewest number of SPOT terms, and if there's any left, we choose those, the one that has the shortest filter length. And if there's any left, we just choose one. Okay, well, here's a design example. We have a particular stop band, pass band, ripple in the pass band, and cutoff level. And we have to make some assignments of these signals. Typically, this is what we do. In the pass band, this has to be pretty small to make this work. And the stop bands can be larger. For that example, we can make, once we've got our samples, we can make estimates of the posterior probability for the number of sine power of 2 terms, something like this. 16 is for the maximum. For our choice, it actually chose one that had 18, and you make go back and calculate the coefficients of the original filter. Here they are. Each of these terms is a sine power 2. So for the shift of 1, we have 2 sine power of 2 terms to make up the z sub 1. If you go back and plot the filter result for that design filter, you can see that it perfectly fits inside the desired upper and lower envelope. And, okay, well, other people have methods for doing this. The problem is that they're really tortuous. They're all optimization methods of one variety or another, and mostly they depend upon starting with an approximate filter design cobbled together by some method or another, and then they try to take that and do some sort of optimization. I guess the first of these is probably in the late 90s, related to annealing, some of these others. The first methods, they often fix something like the filter length. They fix the number of sine power of 2 terms. They don't actually try to design everything. So the only one that's really fully comparable is this hybrid genetic algorithm. That's a recent paper. Designed this, all of these people designed the same example. But you can see the comparison. This is the length. We get the same length as the hybrid genetic method. But this is the number of sine power of 2 coefficients. And you can see we get significantly less. And we can do it with the same number of required bits or shifts. And so this is successful. But the other thing to be said about this is that this thing, to do another problem with this hybrid genetic method, other than this particular low-pass filter, if you want to do a band-pass filter or something, would require very significant fiddling with and changing. I mean, it's something that requires a lot of intervention by the user to make it work. Whereas this thing, once you set it up, you turn the crank, you want a different filter design, you just put in the requirements and it pops out. As I'm trying to say, it's robust. Okay, well, I think I'm done. I'm done. What? Oh, well, no, I think I concluded when I was talking about it. Yeah, I said what I wanted to say. Thank you. Yeah.
So, when you went back to design the prior for your problem, it seems to me that you were somehow expressing maybe what you thought was the cost of each of these individual types of filters.
I wouldn't. There's specifications for any design. Some of them are hard specifications. I mean, your designing something that's got to go into space. It can't be longer than this. It can't weigh more than this. Some of those are set that way. I mean, for some particular reason, you just knew that you couldn't accommodate a filter longer than a certain length. Some of them are set that way. Some of them are just to express. It would be nice. It would lower the complexity of the filter if certain things were true, like the way we assign the prior for the get back there.
So specifically, I was wondering whether this would be equivalent to having a utility function instead on your decision of, like, once you've inferred what the best options are, in theory, then having a cost on your utility of actually choosing specific.
Right, and I think you could do that. And we didn't think very hard about the decision aspect of it. We were more interested on so the decision that we do is a real ad hoc thing. That's just what we do, and we don't claim that there's anything magic or special or actually things that's even particularly a good way of going about it. But that's just what we did.
Another question?
Yeah, I think there's a point here about, and you're alluding to it, about utilities and so on. The point about having the very general calculus we have, good, solid, wide-ranging foundation, is that it doesn't really matter what the application is. We talk about the prior, we talk about the utility function. All these things just factor into the same calculus. You don't even have to think about what you're doing. We're not talking about beliefs about what the thing should be. We're talking about utilities. It doesn't matter. It's the same calculus, it's the same programs, it's the same philosophy.
But I think you make a good point that if in assigning these prior to design things, if you might want to define utility and use utility to derive a particular prior.
Yeah, sure.
Yes.
You had this overcomplete set of filter parameters, which gave you this, let's say, overlapping sum leading to the same values, but it doesn't appear to be possible to exclude that from the very beginning because it's all binary mathematics. So I think there can be a very simple algorithm which restricts the algorithm from the very beginning to a reasonable subset instead of adding later a penalty term.
Yeah, not really, because you don't know. I can explain it. Go back to the original. You don't know. You don't know which one of these terms is associated with which one of these things. I mean, and you do that so that you get a model that you can assign atomic priors to. And if you, because I don't know that this, there's this p, there's a p here, there's a coefficient here. How should I say this? In this sum, I don't know which of these values, which of these ends end up being related to a particular coefficient.
So they are distributed later.
Yeah, I don't have to say, and that's sort of the whole point. This is here. K is definitely an index here. It's an index over these tap positions, right? But this end is not an index over the tap positions, and that's why I have to have this piece of K which takes in and maps it to a tap position. So.
Okay, that appears to be how it is.
Yeah, and that's the whole deal. But if I'm going to use basis, I have to have something that looks like a quote-unquote atomic model, something I can assign an atomic prior to, which is why we do it this way. And this is why I can't use a prior to enforce it, because it would violate being an atomic prior. That's why I had to put it. It's kind of a hack to put it in likelihood, but that's where it can go.
One last question.
I think I would like to come back to this point of the decision of whether your problem can be represented through a utility function, whether it can be done that way. And I would suggest that the answer is yes, it can be done through the same framework can be represented through a utility function.
Which framework?
Your framework using base.
Oh, yeah.
Yes, and it wouldn't change anything. And the trivial solution is once one realizes that Bayesian updating is equivalent to an entropic updating, then the appropriate utility function would be a relative entropy. And so in a sense, you're already doing it. Don't change a thing, it's perfect. Okay? But it addresses this interesting question of, I do not need entropy because I'm using base correctly. That's true. But it's also true that you're already using entropy because you're using base correctly. So, good, perfect.
Let's thank the speaker.